The main purpose parents seem to serve in life is telling you to do things like cleaning your room, shaving the dog, or solving their home improvement problems. In the case of your parents, they expect you to use calculus. This is your house. Well, actually, your house probably looks something more like this, but that's not important. Your parents want you to help them take out the south wall of their house and replace it with a slanted piece of glass so that they can turn it into a greenhouse. They want to get the maximum usable floor space from the sheet of quarter-inch thick ballistic glass that they happen to have lying about. The only problem is that your dad is some height 8 feet tall and prone to bumping his head on things, so any of the floor space that is in an area where the roof is at or lower than his height is considered unusable. Despite your parents owning a badly colored exact replica of Monticello and apparently being rich enough to just blow up part of it on a whim, they don't seem to realize that a square greenhouse would have no unusable space. But they're particularly thick-headed, so we're just going to have to do the calculus. At first look, this is a rather difficult endeavor. You're working in 3 dimensions with multiple variables, and you're trying to maximize the space for your parents to plant their stupid potted plants that you don't really care about, but a closer look tells us that we can simplify it down to a single variable that we can then maximize. The width of the south wall remains constant no matter how you slant the glass, so there's no need to consider it in your calculations. Whereas we originally considered length, width, and height, we're now only interested in length and height. The triangle we're left with can be split into 2 parts, the trapezoid that encompasses the usable floor space, and the triangle that constitutes the unusable floor space. The height of the trapezoid and its total area aren't of consequence because it's the floor space we need to solve for, but the height of the small triangle is necessary for establishing the relationship needed to solve the problem, as we'll see in a bit. We're given several quantities: L, the length of the entire pane of glass; L1, the length of the glass over the usable area; L2, the length of the glass over the unusable area; H, the height of your dad and the height of the unusable area; X2, the floor length of the unusable area; X1, the length of the usable area; and finally theta, the angle between the glass and the ground. X1 is the quantity we're trying to maximize, but we're going to need to do some work to get to the point where we can maximize it. Because we have a lot of unknowns, we need to separate the variables into constants. It just so happens that L and H are the only constants, so we're going to need to get rid of all the other variables in order to maximize X1. We have several useful relationships here. L is equal to L1 plus L2, sine of theta equals H over L2, and X1 equals L1 times cosine of theta. The easiest way to solve this would be to have x1 as the dependent variable which we plan to maximize and have theta as the independent. We're now searching for the ideal angle at which to place the glass in order to gain the most usable floor space. We need to solve so that x1 is isolated. We'll start by rearranging this equation so that L2 equals H over sine theta. Then we can bring that relationship back to L1 plus L2 equals L and substitute it. Next, we'll isolate L1, which becomes L1 equals L minus H over sine theta. Finally, we'll substitute for L1 and get x1 equals L minus H over sine theta times cosine, which can be simplified to L cosine theta minus H cosine theta over sine theta, or H over tangent theta. Now, assuming you have some values for H and L, you can plug them into the graph and find the relative max between 0 and 90 degrees. The graph will probably look something like this. But we can also solve it mathematically. If we derive x1 and analyze the derivative, we can find its relative maximum. x1 prime is equal to negative L sine theta plus H times cosecant squared theta. If we set this equal to 0 and rearrange, we get L sine theta equals H cosecant squared theta. Since cosecant equals 1 over sine theta, we can exchange the cosecant squared for 1 over sine squared theta, then divide the right side by sine, giving us L equals H over sine cubed theta. If we switch sine cubed theta with L, we get sine cubed theta equals H over L. We do a cube root to the other side and get sine of theta equals plus or minus cube root of H over L, but we really want the positive since the angle can't be negative. Now, we take the inverse trigonometric function and get theta equals inverse sine of the cube root of the quantity H, your dad's height, over L, the length of the pane of glass. This is the maximum value for theta, and at this angle the usable floor space will be maximized. You can plug in some random values and test it.